this 31st lecture, we shall solve the questions of class test 2 and we will make concluding discussions on Z transforms. In class test number 2, the first problem 1 was evaluate the following integral using Parseval's theorem. The integral is I equal to minus infinity to plus infinity 1 over 2 pi sinc squared omega t divided by 2 pi d omega. This is to be evaluated using Parseval's theorem. And most of you, I think, have succeeded in this. One recognizes that this, if you treat this as some capital X of omega squared, then Parseval's theorem states that this is equal to integral minus infinity to infinity. This is the energy in the function in the spectrum, and this would be, by Parseval's theorem, would be energy in the time domain, that is xt squared dt from minus infinity to infinity plus infinity. And the only problem therefore is to find out x of t corresponding to this capital X of omega. And this we have done several times in the past, that is sinc of omega t by 2 pi is the Fourier transform of x of t. This is x of omega. This is the Fourier transform x of t, which is a gate function, that is, it is 1 by t for mod t less than, not equal to, there is a discontinuity, mod t less than t by 2 and it is 0 otherwise. That is, it is this function minus t by 2 to plus t by 2 and the height is capital T, no, 1 by t. This was chosen to make the area under the curve unity, and you know when capital T tends to 0, this tends to a delta function. Alright, so x of t is this, and therefore capital I by Parseval's theorem should be minus infinity to plus infinity 1 by t squared, and if you put 1 by t squared, then naturally the integral limits have to be changed from minus t by 2 to plus t by 2, 1 by t squared dt, and this, as you can see, is simply equal to 1 by capital T. So that is the value of the integral. If you wanted to do it, if you wanted to evaluate this integral by ordinary integration methods, it would be much more difficult than what we have done. That is, even if it is a sinc function in the time domain, it is an extremely simple function, so integration in the time domain is much easier. And this is one method of evaluating complicated integrals.
But then do these complicated integrals actually occur?
Oh yes.
So do we want to integrate a sinc function of?
Oh yes, it occurs many times. You have to find out the energy in a sinc function.
So where do we get sinc functions from?
This is the spectrum. It could also occur in a time domain. You know, if the frequency spectrum is close to a rectangular function like this, then its corresponding time domain function is the sinc function because of duality. It occurs many times, and you shall get this sinc function again and again in your communication course, in data transmission, in digital communication, everywhere a sinc function either in the frequency domain or in the time domain shall appear again and again, and therefore it is indeed important. Question 2, there are 5 points in question 1. Question 2 is, a filter has the frequency response h of omega like this. H of omega is a low pass function, from minus 2 pi b to plus 2 pi b, and this value is 1. Capital B I use a different color. Capital B obviously is the cutoff frequency of the low pass filter. The frequency response of the low pass filter LPF is like this, where B obviously, what is the unit? B is in hertz, B in hertz. This is the low pass filter, and to this low pass filter H of omega is applied an input signal x of t, which is given by twice W sinc, once again a sinc function, sinc of 2wt, and you are required to find out the output y of t for two conditions, that is W less than B and part B W greater than B. Well, all that you have to do, well, one can do this problem in various ways, but the simplest one is the following. What you do is you apply the multiplication theorem of convolution, that is x of t convolved with h of t is equivalent to the product of capital X of omega and h of omega in the frequency domain. That is, what you essentially do is you find out capital Y of omega, which is equal to x of omega, the spectrum of the input signal multiplied by the frequency response of the system, and then find out y of t as the Fourier inverse of capital Y of omega. This is a typical problem in linear system analysis. The only thing that one has to notice is the following, that x of t is given by twice W sinc of 2wt. What is the unit of W here? No, it's hertz, because the sinc function gets multiplied by pi. Sinc of x is sin pi x divided by pi x, and therefore W is also in hertz. And that is why if this was in radians per second W, then this inequality would not have made sense, right? Because the units would have been different. W less than B and B is in hertz, so W must also be in hertz. Otherwise, it doesn't make sense. All right. So this is our problem. And if you look at the function, this is a sinc function in the time domain, and therefore the frequency domain by duality, capital X of omega must be a gate function. That is, this gate function is capital X of omega is 1 if the frequency, well, W has been given in hertz. All right. So let's write in terms of hertz. We can also write in terms of, well, we can write like this, capital omega less than 2 pi W, which means that frequency, that is frequency f in hertz, is less than W, and it is 0 otherwise. Once again the sinc function, now the sinc function is in the time domain, so the spectrum is a gate in the frequency domain. It if I look at the spectrum, capital X of omega is like this. Capital X of omega. Now let me plot this versus frequency, all right, because I have to compare with capital H of omega, and no, I can do it versus omega also, there is no problem. 2 pi W, and this is minus 2 pi W, and this is unity. All right. Now I have to multiply this function by another gate function exactly like this, except that I am not drawing to scale. H of omega is also like this, except that this goes from minus 2 pi b to plus 2 pi b. And now you have to multiply the two and find out the Fourier inverse. Now if you multiply the two and you take the first case, that is W is less than B, then obviously y of omega, which is equal to x of omega multiplied by h of omega, shall be simply equal to W is less than B. That's simply equal to x of omega, and therefore which means that y of t equal to x of t, which is equal to what is given, that is twice w sinc of 2wt. All right. On the other hand, if w is greater than b, then obviously h of omega takes over. H of omega becomes 0 before x of omega becomes 0, because w is greater than b, and therefore y of omega simply becomes equal to h of omega. All right, which means that y of t shall now be equal to twice b sinc of 2bt. That's it. That's the answer to the question. This carried 6 points. The third problem, question number 3, was determine the range of permissible cutoff frequencies for the ideal low pass filter used to reconstruct the signal. Well, it's a bit roundabout way. The question is, given this signal x of t equal to 10 cosine of 600 pi t multiplied by cosine squared 1600 pi t. Well, what is the frequency of this signal, cosine? In radians it is 600 pi. 300 hertz. That means 0.3 kilohertz. Similarly, the frequency of this 1.6 kilohertz. No, 0.8 kilohertz. Okay. Now, given this signal, and then it says from its impulse sampled version, that is, you multiply this by the usual p of t, the impulse sampling, and the sampling being carried out at the rate of 4000 samples per second. So, the sampling frequency fs, which is equal to 1 by sampling interval, is given as 4000 unit hertz, 4000 hertz. Now, we have not yet found out the highest frequency, so we have to find out and we have to see. But the question, let me state it again, the question is that this signal x of t is sampled by the usual impulse delta t minus kt, where k goes from minus infinity to plus infinity. This is the usual impulse sampling, and after, well, impulse sampling is done with a value of capital T such that the sampling frequency is 4000. That means every second 4000 samples are taken. The point is, from the sampled version of the signal, you have to recover, that is x, how did you denote the sampled version? xp of t, all right, the sampled version. From xp of t, you have to recover x of t, and you have to find out what low pass filter can be used. What is the low pass filter? What should be the cutoff frequency? fc of LPF. This is what is required. You have to determine the fc of LPF required to reconstruct x of t from the sampled version. And then you have also been asked to sketch capital X of omega and xp of omega, that is the original spectrum and the sample spectrum. And finally, the last question was find the minimum allowable sampling frequency, that is fs minimum. Let me state the problem again. Given this signal x of t equal to 10 cosine 600 pi t multiplied by cosine squared 1600 pi t, this signal is sampled by the usual impulse sampling, that is, it is multiplied by p of t, which is a chain of delta functions, capital T distance apart, such that capital T is given by this relation, that is, sampling is done at 4000 hertz. The resulting signal, which is the xp of t, from xp of t, if you wish to recover small x of t, that is the original signal, what should be the low pass filter cutoff frequency? Obviously, there is a range of permissible cutoff frequencies which you have to determine, and also sketch the spectrum of the original signal and its impulse sample form, the spectra, and finally you have to say what is the minimum sampling frequency that could be used. All right. The solution of the problem proceeds like this. The first thing you do is, given x of t, you express first as a sum of sines or cosines. All right. What you do is 10 cosine of 600 pi t, then cosine squared 1600 pi t. You write this. Well, let me write the signal. Cosine squared 1600 pi t. So first you write cosine squared theta is equal to
1 plus cos 2 theta.
1 plus cosine of 2 theta divided by 2. All right. Then you write cosine A. After you do this, multiply out. Then you write cosine A cosine B. Yeah, what is the formula? Cosine of
A plus B by 2.
A plus B by 2. Is that correct?
No,
Cosine of
A plus B plus cos A minus B.
plus cosine of A minus B
Whole by 2.
whole by 2. That is correct. If you do these transformations, then one can show that x of t can be written in this form. I am avoiding the algebra. X of t is 5 cosine of 600 pi t. Where does this come from? This frequency is unchanged because there is a constant term in the cosine squared. All right. With a multiplication of half. Plus 5 by 2, that is 2.5 cosine of 3800. Where does 3800 come from? 1600 multiplied by 2 is 32. 32 plus 6. So there must appear 32 minus 6 also. So the other frequency would be with the same multiplication, cosine of 2600 pi t. And the spectrum of this, one does not have to take Fourier transform. Spectrum of this is obvious. This is, if we write in terms of f, the frequency, then at DC, is there anything? No. There is no DC component. This is my capital X of omega. Now let's see where the components appear. One is at the frequency 0.3, all right, 0.3 kilohertz. There is an impulse strength
5 by
5
2.
or 5 by 2.
5 by 2.
That is 2.5. Similarly, at minus 0.3, there is an impulse. Minus 0.3, there is an impulse of the same strength. All right. Then at what is the frequency of this?
1.9.
1.9. But before that, there is a 1.3. So at 1.3, and what is the strength now?
1.25.
1.25. Similarly, at 1.9, pardon me, the strength contains a pi. How come?
So because of Fourier transform of cos pi by j.
Okay.
Pi by 2.
All right. There is a factor of pi in all of them, all these strings. Okay. Is this point clear?
Yes.
Okay. So there is a 1.9 at which also the strength is 1.25, and similarly on the left hand side. Let me show it. Minus 1.3, and this F is in kilohertz. This is minus 1.9. Now this is the spectrum of the sample signal, and this is the spectrum of the original signal, and the sampling is carried out at 4000 Hertz. That means 4 kilohertz. So Fs by 2, half of the sampling frequency, is here, somewhere here, 2 and minus 2. And if this signal is sampled, obviously the spectrum shall be a periodic repetition of this, which means that there shall be no aliasing. The samples shall remain distinct. Now let's look at xp of omega. In xp of omega, let's demarcate 2 and minus 2. Let's draw only the right hand side, alright, to keep life simple. We have at point 3, we have at 1.3, these are not to scale. Point 3, I better show a larger one. Okay, 1.3 and 1.9, not to scale. Then the repetition would be around 4. So if this is 4, then there shall be an impulse of strength 2.5 by pi or multiplied by pi? Multiplied by pi.
It will be cancelled.
Alright. Where is the location? 4 minus 0.3. It will be this impulse which will come here. Minus 0.3. So that will be 1 at 3.7. Then 4 minus 1.3. So there will be 1 at 2.7. Alright, 2.7. And there will be 1 at 2.1. And it will be a periodic repetition of this, on this side as well as on this side. So this will be xp of omega versus f, once again in kilohertz. Alright. The point to note is that there is no aliasing, because the original sample, original signal can now be recovered if you use a low pass filter which cuts off anywhere between 1.9 and 2.1. It could be a 2 kilohertz, for example. The pass band could extend from 0 to 2 kilohertz. I could have something like this. It doesn't have to be exactly 2. I could have something like this. Okay, where this is 1 for simplicity, and this is h of omega that is needed to recover, and fc obviously has to lie between 1.9 and 2.1 kilohertz. This is what was meant by range of frequencies, range of cutoff frequencies for the low pass filter required to recover the signal. We can't put it exactly at 1.9. Agreed? Because then we shall perhaps miss the impulse at 1.9. We can't put it at 2.1. We can put it anywhere in between. This is something one has to remember in practice, that the sampling frequency cannot be exactly twice the highest frequency content. It cannot be exactly for practical reasons, because then it is very difficult to make a filter. The filter has to be sharp cutoff, absolutely cutoff from 1 to 0 at that particular frequency, and there is no safety factor. This range is the so-called guard band. That is, you can design a low pass filter in a much more relaxed manner if this spacing was larger. Alright, was larger. But fortunately 0.2 kilohertz is not too bad, 2000 hertz, and therefore one can design a low pass filter to recover the signal. Obviously the minimum sampling frequency, Fs minimum, is obviously how much? 3800, twice the highest frequency content, but you have to make it 3800 plus delta. A delta is a small quantity.
So factor of pi.
Pardon me?
Factor of pi.
No, Fs minimum. Fs, sampling frequency, there is no pi. 3800 hertz, 3800 plus delta hertz. Well, if you put Fs minimum as 3800, the answer is acceptable. In theory, yes, it is acceptable. But for practical purposes, it must be this plus delta. question 4, where most of the people, I think only a few succeeded in question 4. Not many people succeeded, because you forgot one of the maxims that I have been preaching in this class. A picture is worth 1,000 words or 2,000 equations. You forgot to draw the picture. Let me state the problem, then I'll tell you the importance of the picture. The question number 4 was, in figure 2 below, a signal x of n, a discrete time signal, is sampled by the usual impulse sampling, but the impulse is now of the form, the impulse chain is of the form k equal to minus infinity delta n minus 4k. Alright, that means there is an impulse, there is a pulse at n equal to 0, there is a pulse at n equal to 4, n equal to 8, and so on and so forth. Nothing appears at n equal to 1, 2, and 3. Alright, so it is a periodic function with a period capital N equal to 4. Alright, this is the output y of n, and what you are required to find out, the Fourier transform of x of n, that is the spectrum of x of n, is given like this. And so on this side, and so on this side. It's a periodic repetition, and the value is 1 pi by 2 minus pi by 2. This is pi, then this is 2 pi, this is minus 2 pi, pi is somewhere here, minus pi is somewhere here, and so on. This is given as capital X of omega. Alright, so what we have done is we have impulse sampled a discrete time signal x of n by a chain of impulses which occurs at every fourth sample. In between there is nothing. The output is also a discrete time signal y of n, and what you are required to do is to find out capital Y of omega and the corresponding signal y of n. That was the question. Now, the solution of this problem, in fact, such a problem has been solved in the class. If you refer to pages 316 to 319 of Oppenheim, Wilsky and Young, it has been solved. That is, we have shown, not exactly this problem, but we have shown that a sequence like this, k equal to minus infinity to plus infinity, delta of n minus k capital N, a general signal, has the Fourier transform dtft, has the Fourier transform which is equal to summation 2 pi ak. We had come through the Fourier series ak, then delta of omega minus 2 pi k by n. Alright, these are the Fourier pairs. And ak here, k goes from minus infinity to plus infinity. Ak is equal to 1 over n. Alright. Now, if I apply to the particular problem at hand, then my capital N is equal to 4, and therefore my capital P of omega will be equal to twice pi divided by 4, that means pi by 2, summation k equals minus infinity to plus infinity, delta of omega minus, again, pi k divided by 2, pi k divided by 2. And what I have to do is, since I am multiplying x of n by p of n, the corresponding Fourier transform would be 1 by 2 pi, this factor some of you ignore, 1 by 2 pi, then the convolution of p of omega with x of omega. And you know, convolution of x of omega with a delta function, omega minus, let's say, pi k by 2, is simply equal to capital X of omega minus pi k by 2. That is this same spectrum shifted by the amount pi k by 2. If you utilize this and this, then obviously capital Y of omega becomes simply equal to pi by 2 multiplied by k equal to minus infinity to plus infinity, capital X of omega minus pi k divided by 2. Oh, 1 by 2 pi factor. So this would be 1/4. This should be 1.
From minus infinity to plus infinity, y omega will blow up. So in xn to y omega, its Fourier transform is not it's a convolution over a period of 2 pi, not from minus infinity to plus infinity.
Because its signal is periodic.
Okay. What I have done here is, and then it repeats.
And then it repeats. Yes.
You see, you convolve over one period, then it repeats. I forgot about periodicity. What I did was I convolved term by term. It's an infinite summation, so every term I convolve. Alright? I could do it the other way around also. I could do it over one period and then extend.
So, but then what is the guarantee that you will get the same thing?
What is the it is guaranteed.
Y omega, when you write in this form, it's going to blow up, sir.
So this quantity will blow up, sir.
Yes, sir. This has to, sir. This has to.
Sir, look at the X omega you have given us. It will blow up, sir.
Okay.
So you cannot sum these triangles.
No, answer me one question. Is this answer wrong?
Yes, sir.
Yes, sir.
Wrong. Why? What is
Because
it?
it's not a convolution, it's a periodic convolution.
X omega is periodic,
Because
Okay.
so it will repeat after every 2 pi.
So each repeats for only 4 times, not infinite number of times.
Each repeats only 4 times. That is in the time domain. Yes, the delta function.
Discrete times of
Yeah.
when you multiply two signals in the time domain.
Okay.
In the omega domain, the Fourier transform is the convolution over a period of 2 pi, not over the entire range of omega. So that's why, sir, when you wrote x and y n corresponds to 1 over 2 pi x omega star y omega.
Yes.
Sir,
This
this is only over a period of 2 pi.
The integral is from 2 pi.
So you just add 4 x omegas, 4 shifted versions of x.
K equal to 0 to 3.
Because in a period of 2 pi,
That is wrong.
when delta functions are spaced at an interval of pi by 2, you will encounter 4 such.
4 such functions.
Yes. Yeah.
So why should it blow up then?
No, only 4. Now it blows up.
You are convolving infinite.
So if you write the actual integral, you will see that there you are going wrong, sir. If you write the actual integral, you will.
So now a picture, if you draw a picture, we'll get to know it better.
Okay. If I draw this picture,
Yes, sir.
Yes.
this picture. Okay.
That picture also, the one we are seeing.
Alright. Now, if this expression is wrong, then obviously the picture will also be wrong. Okay. My contention is, what you are saying is that this convolution should be over one period.
Yes.
It is a periodic convolution. Okay. If it is over one period, what shall be the picture? Alright. Let me draw over one period. What I have is x of omega okay, one period means from minus pi to plus pi. Okay, so this is minus pi by 2, then this is pi by 2, and then at pi by 2 once again is another center for the triangular waveform, and therefore I shall have something like this, where this shall be pi, and similarly on this side this shall be minus pi. Alright, this is over one period. Now this pattern repeats. This pattern repeats, and obviously there is aliasing, because one triangle comes and jumps over the other, and therefore in the next period, where does it start?
Pi by 2.
From pi by 2, and therefore it goes like this, and it goes like this, and ad infinitum.
Yes. Sir, this is right, sir, but
This is our,
omega is equal to this is wrong.
This is a result of 4 convolutions only.
this is a result of periodic convolution.
This is a result of periodic.
Yes,
convolution.
But what
Okay.
you are writing is the of infinite.
Okay, okay. I understand what you are saying. That is correct. Alright. So what should we put the limit
0 to
as?
3. 0
K
basically
equal
over n.
to?
Over n.
Minus 2 to plus 2.
Minus 2 to plus 1.
Plus 1. Over a range of
Over n.
Over
total
n.
of 4.
Yeah.
Not
So,
so minus 2
0
to
to
2 will have 5. Minus 2 to 2 will have 5.
0 to 3 or over n.
yeah, okay. Minus 2 to 2 will be 5, yes. Alright. I still leave a question mark here. You think it over about the limits. Alright. Now, it is obvious that capital Y omega is a constant. It is obvious. Because of aliasing, capital Y omega is simply equal to 1/4. Which means that Y of n is equal to 1/4 delta. This is the answer. This is the correct answer. Capital Y omega. Now, many of you,
So how does that come out to be a constant 1/4?
oh, this is obvious from here. You see, you add them up. At this point, for example, it's 1/4. And this is a linear variation. So, you go like this, this also decreases by the same amount. And therefore, the sum always remains 1/4. Okay, many of you did not draw the picture. You put an expression for capital X omega here and then ended up in a mess. Some of you tried to obtain the inverse Fourier transform by using the formula 1/2 pi and ended up in a bigger mess.
You have checked this question, sir.
Pardon?
This question.
I have checked this question. Let me give you the distribution of marks. I gave 4 for an expression of for y of omega. That is 1/4 summation. Alright. 4 marks. 3 for capital Y of omega. That is to show that it is equal to 1/4. And 1 for Y of n. This was my distribution. Alright. Question 5. Question 5 was the simplest of all. Question 5 says, a linear LTI system is described by the difference equation 1/b y of n equal to a x of n minus 1 plus x of n plus a x of n plus 1. And the first question was, what is the frequency response of the system, h of omega? And obviously, if I take the Fourier transform of both sides, 1/b y omega is equal to a, by the Diller theorem, it is e to the minus j omega, capital X of omega, plus capital X of omega, plus a, no, I beg your pardon, a has to come in, plus a e to the plus j omega, x of omega. And therefore, h of omega, you can simplify this as b times 1, capital H of omega is y of omega divided by x of omega, b times 1 plus twice a cosine omega. This is the frequency response, and I assigned 2 points for this. Part B is DC response is specified as unity. Now, many of you, I understand, had a problem with this DC response, the term DC response. Well, DC is the usual sense. DC has 0 frequency, that is capital omega is equal to 0. Whether it is small omega or capital omega, 0 frequency corresponds to 0 frequency in both the digital and analog domain. And therefore, what is specified is h of 0 equal to 1. And therefore, B is equal to 1 over 1 plus 2a, and there was assigned 1 mark, I think, for this. This was 1 mark. Part C was for a equal to half, you are required to determine and sketch the magnitude and phase response. Well, a equal to half obviously leads to b equal to half. B is 1/1 plus 2a. And therefore, capital H of omega is half 1 plus cosine omega. Many of you drew a plot of cosine omega, drew a plot of unity, added the 2, divided by 2 and so on. But why didn't you see that this is simply equal to cosine squared omega by 2? and the magnitude is cosine squared omega by 2. It cannot go negative, and the phase therefore is identically equal to 0, and therefore the plots shall be like this, or it is cosine omega by 2. Cosine squared omega by 2 is simply a full rectified sine wave like this, but pardon?
So this thing is for mod of cos omega.
This is cos square.
This is cos
Okay.
square.
This is cosine square.
This is mod of cos omega. Cos square omega is differentiable everywhere.
Yes, sir.
So we can't have kings at whatever zeros.
Except
So it must be
sort of
smooth.
shifted above.
Cosine squared omega by 2 is differentiable everywhere.
Yes.
What about the differentiation here?
Differentiable.
At omega equal to pi by 2.
This point is just like the point at 1.
It's a minima.
Okay. So it goes like this. Why does that occur? Because it is cosine omega, which is a smoothly differentiable function, plus 1. So it's simply shift and then scaling. Cosine omega is differentiable everywhere, and therefore there is no reason why cosine squared omega by 2 should not be differentiable. After all, these two are identical. Cosine omega is differentiable everywhere, and Nitin is quite correct, Pankaj, I beg your pardon, is quite correct that the whole thing, cosine square, when it changes shape, when it changes its form, the differentiability does not disappear. So there will be no kink. This will be smooth. And the values would be, this would be what? Pi minus pi, isn't it right? And this would be 2 pi. So this would be
Pi by 2, sir. It's periodic over pi.
cosine squared omega by 2. So omega,
सीन क्या है? पाई पे 0 है.
this is okay.
It's okay.
This is okay. Cosine squared omega by 2, which is 0 at omega equal to pi, 3 pi, and so on. And therefore this is the plot of mod h of omega, and the phase term many of you ignore. Well, that's why I assigned 1.5 mark to this, and for the phase half mark. But you must show the phase, and you must show it distinctly. Capital omega, angle of h of omega. How do I show the phase? I can say it's 0 everywhere, or I show by a different color.
So we don't have different colors, sir.
Why don't you?
Share of the paper.
Why don't you have different color? Bring a red pencil, red pen or something. You must show it.
Pen is not a red pen, sir. That's meant only for examiners.
Green layer, black layer.
Has IIT ever told you that red is disallowed? No, we don't have such thing.
Exam it was disallowed.
Oh, entrance exam. Entrance exam is like a gate. Once you enter it, you behave
So
like
gate is for PG, sir.
free
J,
citizens.
sir.
All right. The last part of Z transforms is the unilateral Z transform. Exactly like the unilateral Laplace transform. Unilateral Z transform is defined like this. If x of n is a sequence, arbitrary sequence, may extend from minus infinity to plus infinity, the bilateral Z transform, now we shall distinguish between bilateral and unilateral by the subscript small b and small u, xbz is defined as summation x of n, z to the minus n equals minus infinity to plus infinity as usual, and the unilateral Z transform capital X u of z is defined as the lower limit is 0, it starts from 0, n equal to 0 to infinity x of n z to the minus n. It does not mean that x of n is a one-sided signal. It does not mean that x of n starts at n equal to 0. It only means that you ignore all samples of x of n prior to n equal to 0. In other words, x u of z is the same as x b, no, I beg your pardon, is the same as bilateral z transform of x n u n. Is the point clear? X of n may be anything. We simply cut it off. We simply cut off all the samples for n less than 0, and that is the that is the unilateral z transform. If we have, let's say, x of n equal to a to the n u n, all right, then its bilateral z transform, as you know, is 1 by 1 minus a z inverse mod z greater than mod a. What is its unilateral z transform? It's the same. It's the same as this, because this signal does not exist for n less than 0. But we can think of a signal which does exist before n equal to 0. For example, take x of n as a to the n plus 1 u of n plus 1. This signal starts at n equal to minus 1, and therefore if I take x b of z, the bilateral z transform, what shall this be? You know, a to the n.
z by 1 minus a.
That's right. It would be simply an advance by one sample, z by 1 minus a z inverse with mod z greater than mod a. You understand how we got this? A to the n un is 1 by 1 minus a z inverse. So you change n to n plus 1, then you have to multiply by z. If you have changed n to n minus 1,
Z inverse.
then you have to multiply by z inverse. Alright, so we get this. Now, if I find out unilateral z transform, that would be, let's see what this becomes. N equal to 0 to infinity, a to the n plus 1, u n plus 1, z to the minus n. Now, obviously, since un plus 1 starts at minus 1, the value between n equal to 0 and infinity is simply 1, right? Of un plus 1, the value is 1 between n equal to 0 to infinity, so I could as well replace this by 1. And you can easily see that this is simply a divided by 1 minus a z inverse, with the same region of convergence, mod z greater than mod a. Otherwise you cannot sum this up. But you see the difference. There is a factor of z here, there is a factor of a here. And therefore, the unilateral Laplace transform can be quite different from the bilateral Laplace transform. The question, not Laplace, z transform. The question is, if you can do it bilateral, why worry about unilateral? Well, unilateral z transforms are useful in solving difference equations with initial conditions. And we shall take a couple of examples to illustrate this. The first example that we take is, well, before we take an example, we have to see a couple of differences between unilateral and bilateral. You know that if y of n is x of n minus 1, then capital Y b of z is simply z inverse capital X b of z. Alright? This you know, delayed by one sample. On the other hand, the unilateral Laplace transform, unilateral z transform is not given by simply this formula. There is added to it an x of minus 1, x u of z. This is one of the differences, and this is what is useful in solving difference equations. To show this, let's consider y of n equal to x of n minus 1, and we have capital YZ equal to n equals 0 to infinity capital X of n minus 1 z to the minus n. I can write this as x of minus 1 plus, okay, n equal to 0 corresponds to x of minus 1 plus n equal to 1 to infinity x of n minus 1 z to the minus n. And we play the usual trick, that is, we put n minus 1 equal to r, then this becomes, n becomes equal to r plus 1, and this limit changes from n equal to 1 to r equal to 0, and this obviously becomes z inverse times capital X u of z, and that's the proof. This is unilateral Laplace transform, y u of z. This is the difference one has to remember. That is, the unilateral Laplace transform, if the function is delayed or advanced, will be quite different from the bilateral Z transform. As another example, suppose the signal is x of n minus 2, then you can show that y u of z is equal to x of minus 2 by the same procedure, simple algebra, plus z inverse x of minus 1 plus z to the minus 2 capital X u of z. On the other hand, if it was bilateral, then these two terms would have been absent. And this is what is useful in solving difference equations. We will take just one example. This is an example from the text.
So what about x n plus 1?
We have already done this. X of n plus 1. Right. Since he has raised the question, z to the minus n, summation n equals 0 to infinity. Alright. This I can write as x of 1 plus summation x of n plus 1 z to the minus n equal to 1 to infinity. And we do the same trick. N plus 1 equal to r.
So
it doesn't work.
It should be the
I
other
think
way
you
around.
should write as n equal to minus 1 to infinity and subtract x.
X of minus 1 should be subtracted. X
What
of
is
minus 1 should be
Subtracted.
subtracted.
X of minus 1 to z.
But we don't require x of n plus 1 in difference equations.
why not?
In difference equation, we just consider delay.
No, you may also consider advance. Why not? For example, just a minute, y of n minus half y of n minus 1 equal to x of n minus half x of n minus 1. I could as well write this equation like this: y of n plus 1 minus half y of n equal to x of n plus 1 minus half x of n. Alright? I could do that. The question is, what is the z transform unilateral of x of n plus 1? Well, it's a good question. Let us see what this is. N equal to 0 to infinity, x of n plus 1, z to the minus n. Now, one of you said that why don't we take x of minus 1? X of minus 1, where does it occur? At n equal to 0, it is x of plus 1. So, what I want
So we need the limit to go from minus 1 to infinity.
No, the definition of unilateral z transform is n equal to 0 to infinity.
That's true, but we need to add and subtract a term.
Why?
So in the last example, you did the same thing, so to get
We need to add and subtract. We need to add n is equal to minus 1 term and subtract
So
it.
when we put n plus 1 equal to r,
Then
we get limit to minus 1 to infinity.
Okay, n plus 1 equal to r. Let's do it this way. If that is what you want,
Yes, sir.
then n goes from, n becomes equal to
r minus
r minus 1. Alright, so what we have is x of r, z to the minus r, then a multiplication by z, and this goes from n equal to
minus 1.
minus 1 to infinity.
R equal to
R equal to minus 1 to infinity. Now this is equal to Z times, you have to put R equal to 1, or R equal to minus 1. That's
X of 0. Plus 1. Minus of X of 0. Separate out the R equal to minus 1 term and then it goes from 0 to 0.
Alright, let's look at this again. Infinity R equal to minus 1. There is no.
So it's R equal to plus 1.
R equal to plus 1.
R equal to plus 1.
That is correct. R equal to plus 1. Oh,
We need to add in fact R equal to 0 now.
this is where we are making a mistake. Yeah, you will get the same result. This is equal to Z, small r equal to 0, x of r, Z to the minus r, minus
X of 0.
X0.
x sub 0. And therefore this is equal to Z capital X sub Z minus x sub 0. How is this result different from the previous one?
By X is 0.
When x of n minus 1 was taken, the result was x of minus 1 plus the inverse capital X sub Z, right? Now, when x of n plus 1 is taken, the result is x of
Z times C. Z times.
okay, it is quite different. Z times capital X sub Z minus x sub Z. Okay. So it does occur, Pankaj. N plus 1 occurs. But let me assure you,
Any equation in form of x of n minus 1, so we don't require it.
no, you can write it in this form. But I assure you, even if you solve this equation, you will get identical results. It is usual practice to take delayed samples rather than advanced samples. Why? Causality. Because physically, an advanced operator is not realizable. It's a delay operator which is realized. And therefore, one always goes back and converts an equation in terms of delayed samples. The initial conditions usually are also on delayed samples. We shall next time work out one or two examples of Z transforms and start our discussion on random signals and systems.